Okay. So, next will be in another example, another 3 or 4 examples, and with that we will close the single phase transformers, right. So, it is given that look at the pointer, a 100 kVA 440 220 volt single phase 50 hertz court type transformer has an efficiency of 98.5% when supplying full load at 0.8 power factor lagging, and an efficiency of 99% when supplying half load at unity power factor. Find the iron losses and copper losses at full load, right. So, this is the problem. So, now with iron loss is equal to Wi and full load copper loss say Wc. Full load means that x is equal to 1, right. I mean it is meaning is something like this, right. Meaning is suppose x is equal to, you write kVA by kVA full load, right. This way if you write, that is suppose transformer is rated some kVA, right, and the kVA at which kVA it operates. So, ratio of this thing will give you the your x, right, the loading factor say. So, if it is kVA is equal to kVA FL, then x is equal to 1. So, that is why it is written here x is equal to 1, right. So, therefore, we know this derive this formula. So, efficiency is 98.5%. So, 0.985 is equal to your this is the 100 kVA transformer, right. So, 100 that is your into 1000 into 0.8 power factor and x is 1. So, it is not shown here, but multiplied by 1, right. They are divided by this same value plus iron loss plus your copper loss Wi plus Wc. So, if you after simplification, if you simplify this, then it will be 0.985 Wi plus 0.985 Wc is equal to 1200. This is equation 1. Now, when output of transformer half load with unity power factor, half load means kVA by 2, right, into your unity power factor 1. This 1 is unity power factor, and 100 kVA transformer half load, the half into 100 into 1000 into 1. So, 50 into 10 to the power 3 watt, right. Therefore, at that time efficiency was 99%. So, 0.99 is equal to then 50 into 10 to the power 3 divided by 50 into 10 to the power 3 plus Wi, and your copper loss will be half square, because we know that your copper loss is equal to your x square Wc, and x it is half load. So, x is equal to half. So, half square Wc, right. Therefore, let me clear it. Therefore, 0.99 Wi plus 0.2475 Wc is equal to 500, that is 2, equation 2. So, solving equation 1 and 2 we get Wi is equal to 267.3 watt and Wc is equal to 950.9 watt. So, this is iron loss and this is copper loss, this is the answer. Here next is you will solve it. I have made double dash, that is, it is not example, it is an exercise for you. You have to calculate the voltage regulation of a transformer having copper loss of 2% of the output and the reactance drop of 5% when power factor is 0.8 lagging and 0.8 leading. You will use that formula, regulation formula, accordingly you will do it. This answer is not given, but this will solve it. Now, next one is that this is the example 13. Here a single phase step down transformer has a turns ratio of 3, that is K is equal to 3. The resistance and reactance of the primary winding are 1.2 ohm and 6 ohm, and those of the secondary winding are 0.05 ohm and 0.03 ohm respectively. If the high voltage winding is supplied at 230 volt with low voltage winding short circuited, right, find the current in the low voltage winding, copper loss in the transformer and power factor. It is given that if the high voltage winding is supplied at 230 volt with low voltage winding short circuited, you have to find out the current in the low voltage winding, copper loss in the transformer and the power factor. Already you have studied open circuit test and short circuit test, right. So, in this case turns ratio is equal to K is equal to 3. High voltage side is primary, say, low voltage side we define as secondary. Here it is, look at the cursor, right. So, R1 is 1.2 ohm, X1 is 6 ohm, R2 is 0.0 ohm, X2 is 0.05 ohm, X2 is, it is corrected, X2 is equal to your, here it is 0.03 ohm, right. So, here it is your point, here it is not 0.3, just hold on. So, it is 0.03 ohm, right, 0.03 ohm. Now, so in this case, so refer to high voltage side, your RE1 is equal to R1 plus K square R2. It is referred to high voltage side the way we have seen it. So, R1 1.2, K is 3, so 3 square into 0.05, 1.65 ohm, and this one X1 plus K square X2 6 plus 3 square is actually 0.03, right. So, all corrections have been made. So, 6.27 ohm, right. So, impedance is equal to root over RE1 square plus XE1 square. So, it is becoming actually 6.48 ohm, right. So, now the circuit in the high voltage winding, current in the high voltage winding where low voltage winding is short circuited. That means, short circuit current is ISC is equal to VSC upon JD1. It is given 230 volt divided by 6.48. So, it is actually 35.47 ampere. Now, we are neglecting I0, right. So, if you neglect I0, then from the transformer we have seen I1 is equal to I2 dash is equal to same current 35.47 ampere. Now, current in low voltage winding, the transformation ratio will use I2 is equal to K into I2 dash, I2 is equal to, right. So, K is 3, so it will become 106.4 ampere. So, now total copper loss if you see WSC will be I1 square RE1. So, it is 35.47 square into 1.65. So, it is coming 2076 watt, right. And here it is your what you call, and another thing we know the VSC ISC cos phi SC is equal to WSC, I mean VI cos phi is equal to W, same relationship. So, V is 230 volt, current is 35.47 ampere, we have to find out cos and is equal to 2076. So, it is coming actually 0.254 the power factor. So, this is very simple thing. Only thing is that if you look into this, that current in the low voltage winding, it is actually 106.4 ampere, quite high, right. So, if you look into the problem, that a single phase step down transformer, this the resistance and reactance of the primary winding, all this given, and if the high voltage winding is supplied at 230 volt with low voltage winding short circuited, find the current in the low voltage winding. So, look at that, in the current in the low voltage winding, this intentionally I took this problem, it is coming 106 ampere. So, in your laboratory you may not have that ammeter to measure this high value of current, right. So, but intentionally we took it, right. So, anyway, so next is your a single phase 3 kVA transformer 230 by 115 volt 50 hertz transformer has the following constant R1 given, X1 is given, R2 X2 also given, and RC, that coal loss component resistance is given, and magnetizing component your reactance is given, right, everything is given. Now, what would be the readings of the instrument when the transformer is connected for open circuit test, then short circuit test? In both the tests, supply is given to high voltage side, right, supply is given both the cases to high voltage side. Now, open circuit test, V1 is equal to 230 volt, K is equal to the turns ratio 230 or voltage ratio 230 by 115 is equal to 2. So, directly you can write all these problems you have solved like your single phase circuit. So, IC is equal to your V1 upon RC. So, 0.383 ampere, circuit is not done here because it is understandable, right, and IM is equal to V1 upon XM. So, 1.15 ampere. Therefore, I0 is equal to under root IC square plus IM square. So, it is coming 1.212 ampere. Now, input on no load to high voltage winding will be V1 into IC, that is the input at no load condition. So, it will be 230 into 0.383. So, it is basically 88.09 watt, approximately your 88 watt, right. Now, hence the readings of the instrument are voltmeter reading 230 volt, ammeter reading 1.2 ampere, and wattmeter reading will be 88 watt, right. Now, short circuit test, here K is equal to 2. So, RE1 is equal to R1 plus K square R2. So, compute all these things, right. So, you will get 0.66 ohm, and here it is XE1 is equal to X1 plus K square X2, you compute, you will get 0.8 ohm. Now, JD1 you compute, you will get 1.037 ohm. Full load current in the your high voltage winding, it is 3 kVA transformer. So, I1 is equal to 3 into 1000 by 230 is equal to 13.04 ampere. Now, VSC under short circuit condition, voltage is I1 into JD1, you will get it is 13.5 volt, because short circuit test is requires very low voltage, right. So, VSC will be 13.5 volt. So, and your WSC, that under short circuit condition the copper loss I1 square RE1, it is coming 112 watt. So, therefore, the reading of the instrument are voltmeter reading will be 13.5 volt, ammeter reading will be 13 ampere, and wattmeter reading will be 112 watt, right. So, your now this is the last problem I think for the transformer, it is an auto transformer. Now, these are very simple thing. So, a 11.5 kV upon 2.3 kV single phase auto transformer when used as two winding transformer has the rated output of 100 kVA. Now, if the two windings of the transformer are connected in series to form as auto transformer, find the possible voltage ratio and output, right. So, this is the problem. So, how we will do it? How we will do it? That two possible connections are possible, right. Here it is the auto transformer, it is A, this part is B, and this center here some part is C, right. So, same as before, this current is I 1, the upward direction is I 2 minus I 1, and this is the current going to the load, say I 2. Now, BC portion say if it is 11,500 volt, say this is my V 2, this is the BC portion, look at the cursor pointer here, BC is equal to your V, that is if it is so, it is 2300 volt V 2, and AC, that is A to C, it is your 11,500 volt, right. If we think it as a your what you call two winding transformer. So, BC is this much 11,500 volt, and AC your what you call, you have taken 2300 volt. Now, another one case is BC is equal to your 11,500 volt, in that case this is V 2, this is one possible connection. Another you can take AC 2300 volt, another is BC 2, if you take BC 2300 volt, then AC will be 11,500 volt. Just your what you call, just two possible connections possible, right, with this. So, now in this, suppose for the first case, in this connection where V 2 is equal to 11,500, that is first case means this one here, this one BC 11,500, that is equal to V 2, and AC 2300 volt. So, in this case V 2 is equal to 11,500 volt, therefore, V 1 you add it up, right, that is your add it up, that is your A to B, right. So, in this case it will be 11,500 plus 2,300, 13,800 volt. Now, therefore, the voltage ratio your K will be 13,800 upon 11,500, 138 by 115, right. And your what you call the transformers, the rating is 100 kVA, it is given. Therefore, I 2 minus I 1 into V 2 is equal to 100 into 1000, right, because it is kVA, we are converting it to volt ampere. Therefore, I 2 minus I 1 you will get 8.7 ampere. Again, V 1 minus V 2 into I 1 is equal to again 100 into 1000. So, from which you will get I 1 is equal to 43.5 ampere. Just see the theories for auto transformer whatever has been done, right. So, now in the therefore, you can get I 2 is equal to 8.7, right, from here, from this equation I 1 we got 43.5. So, I 2 is equal to 8.7 plus this I 1. So, it is coming 52.7 ampere. KVA rating of the auto transformer is given by V 1 I 1. So, substitute all these values, you will get 600 your KVA, right. So, this is 13,800 into your 43.5, this is 13,800, this is 43.5 divided by 1000, you will get 600 KVA. Or V 2 I 2 if you make 11,500 into 52.7 by 1000, here also you will get 600 KVA, right. Now, similarly, the volume of auto transformer you know 1 minus 1 upon K dash volume of two winding transformer, but K dash is equal to V 1 upon V 2, right, that is 138 by 115. Therefore, volume of auto transformer will be 1 minus 115 by 138 into volume of two winding transformer. Therefore, volume of auto but volume of two winding transformer will be 0.17, right, there that is the answer. So, with this your what you call with this single phase transformer we have concluded. Things are very simple, only thing what portion you have to concentrate, that is open circuit test, short circuit test, then your auto transformer, right, comparison of the volume of two winding transformer and auto transformers, right, and equivalent circuit and transformation, and the efficiency as well as the all day efficiency and the voltage regulation for at unity power factor, lagging power factor and leading power factor, right. So, things for single phase transformer is very simple. So, next we will start for your what you call that 3 phase induction machine. It will be very only at first year level. So, it is just a basic portion, right. So, 3 phase induction motor will start. So, it is actually for what particularly at the basic level only little bit will be covered, right, and just see how is it. And before making this your what you call 3-phase induction motor, I will tell at the beginning that whenever you will study this in your college, see your laboratory, that an open induction machine, wound rotor induction machine, as well as squirrel cage induction motor, both wound rotor as well as squirrel cage induction motor. It is open thing. See that stator part, see your what you call the rotor part, because from here with diagram you perhaps visualization will be slightly based on your imagination, but in the laboratory definitely you have that your open stator, open rotor separately, such that you can see on your eyes that exactly what it is, right. So, this is the thing. We will go for single phase transformer. So, hopefully that basic principle of that your induction machine, hope it will not create any problem for you. Things are not difficult one, but only basic purpose at first year level. So, 3-phase induction motors are the motor most frequently encountered in industry. They are simple, low priced, easy to maintain. I mean, that is the thing, and you will find in all the industries, right, you will find the induction motors are there, right, because this is without that nothing will move in the industry. Induction motors are there. So, they run at essentially constant speed from 0 to full load. Sometimes constant speed means sometimes we make it as a meaning is synchronous speed. So, sometimes we call it as a constant speed, right. So, so the 3-phase induction motor has two main parts. One is stationary part, that is called stator. Another is a rotating part or revolving part, we call it as rotor, right. So, the rotor actually is separated from the stator by a small air gap, which ranges from 0.4 millimeter to 4 millimeter depending on the power of the motor. So, there is a gap in between the stator and rotor, and that gap we call air gap, right. So, later we will see the power is transmitted from the stator or to rotor through air gap. So, now the stator actually consists of a steel frame which encloses a hollow cylindrical core made up of stacked lamination. I mean, this photograph I have taken from a book, and this is a photocopy, looks very little bit black because of this photocopy, and these are terminals taken out. So, this is actually your steel part, and inside that you will be steel laminated, right, and when you go inside, these are the slots where 3-phase windings are there. I said that see in your what you call in your laboratory, just to see, have a just to see how the stator is, the rotor is in a your what you call. Similarly, for your power plant, you use synchronous generator. There, if you see your what you call the design of this synchronous generator, I mean when they are repairing or something, you will find it looks so beautiful that your what you call the design for synchronous generator in the power plant, right. But anyway, this is induction motor is a smaller size. Synchronous generator we have a very long rotor, right. In any way, so these windings are placed, how it is placed, these are the slots, all these things that you will just I suggest that see your what you call your laboratory, that your stator part, that when machine is open, definitely some machine will keep it open for your what you call for your realization of this construction. So, the stator consists of a steel frame, I told you, which encloses a hollow cylindrical core made up of stacked laminations, right. Here it is, and this is your steel part, right. So, a number of evenly placed slots punch out of your what you call internal circumference of the lamination, provide the space of for the stator windings. So, stator windings are here. So, I repeat again, see in the laboratory just to see this thing. And before saying anything, that you have this is a 3-phase stator. No, in the transformer the flux was a time varying, right. The difference is that the transformer is a static device, it is a rotating device, but in the case of transformer the flux was your time varying, right. In this case, that in your stator 3-phase, if you supply the power, we have studied 3-phase circuit. So, 3-phase windings are there. So, it will create a 3-phase your what you call rotating magnetic field, but rotor not here, rotor I will show you separately, right. So, 3-phase magnetic field, as soon as it creates because of this your what you call that if we neglect the leakage resistance and reactance like transformer, then a voltage also will be induced in the stator winding in each phase, right. So, this is stator of 3-phase induction motor. So, in this case The rotor is also composed of punch lamination. These are carefully stacked to create a series of rotor slots to provide space for the rotor winding. So, here also I have taken from a book. This figure looks black because of the photocopy. So, this is actually squirrel cage motor. So, this is the squirrel cage rotor rather, right, and here whatever see some kind of bar kind of things, it is squirrel cage rotor. The slots are there and bars actually are placed into that, and for each and both end of this rotor actually your what you call it is welded by a copper because this is made of your what you call copper. So, both sides are your what you call bunched together and welded such that it is short circuited itself. So, why we will see later. So, this is squirrel cage rotor. I suggest in your laboratory see the open induction machine, definitely it will be there, right, that just that you can have a better visualization. So, we use two types of rotor windings. One is that conventional 3-phase windings made of insulated wire, that we call wound rotor induction motor. Some circuit diagram we will show it later. Another is a squirrel cage winding, that is squirrel cage induction motor, right. So, but ultimately operating principle of both the things are same, final operating principle is same, but wound rotor case we will see through slip rings. Your later I will show you circuit diagram that your resistance can be connected, and at the time of your what you call at the and finally when it slowly resistance will be cut down and all these things will be short circuited together. So, rotor actually for induction machine, right, rotors are short circuited, right, it is a self starting. So, how? So, a squirrel cage rotor is composed of your what you call bare copper bars. There the bar I was showing in the diagram, right, slightly larger than the rotor, which are pushed into the slots. I suggest you see in that your what you call in the college that this thing your open machine, and then you will easily understand. The opposite ends are welded of two copper endings, so that all the bars are short circuited together, right, it is a short circuit. The entire construction bars and endings your resembles a squirrel cage from which the name is derived. Later we will see this, right. In small and medium size motors, the bars and endings are made of die cast aluminum molded to form your what you call an integral block. Now, and wound rotor case we will give you the circuit diagram later, has a 3-phase winding similar to the one on the stator. The winding is uniformly distributed in the slots and is usually connected in a star, right. The terminals are connected to 3 slip rings which turn with the rotor. With that circuit diagram I will show you, the circuit diagram I will show you later, right. So, the revolving slip rings and your associated stationary brushes enables us to connect external resistors in series with the rotor windings, right. So, the external resistors are actually mainly used during the startup period. Under normal running condition, the 3 buses are short circuited, right. Under normal running condition, the 3 buses are short circuited. So, when you do experiment, particularly in your second or third year induction machine experiment, at that time wound rotor machine definitely will see. So, when you will do the laboratory experiment, at that time you can see this, but I am not sure whether you will do the same experiment the first year or not, right. So, but these are the thing, but if you are a pure electrical engineer, then you will definitely see it in your second year or third year electrical machine laboratory, right. With this, thank you very much, we will be back again.